In the last video, we were talking about our vocabulary terms in relation to our periodic functions. So as a reminder, a periodic function is any function that has a repeating pattern or over a horizontal length. Within that function, whatever pattern is repeating, we're referring to that as a cycle. The horizontal length of that cycle is called the period, and how many times we see that cycle in a given picture or over a given period of time, we would call the frequency. Now, anything that's going to rotate or repeat over a period of time should be a periodic function. So we're just going to talk about some real-world examples of this. So this first one is dealing with a bicycle pedal. So I want you to pause the video, read through number 3, study this picture, and then fill in this chart. Okay. All right, so as we are looking at this, we are trying to figure out what this graph would look like if we graphed it on our normal Cartesian plane. So if I have a graph that would look like this. Okay. So as I'm looking at this, we are starting at our bike pedal at the top, and then at a half second, my height would be 11. Down here at 1 second, my height is 4 from the ground, and then I'm just continuing to find those heights as we're pedaling around. And it takes me a total of 2 seconds to go 1 full revolution. So we're just going to fill in this chart using our times here based on where our height would be at depending on which part we're on. So at 0 seconds, I am at 18 inches. A half second, we are at 11. 1 second, we are at 4 from the ground. 1.5, we are back to 11. And at 2, we are at 18. So now when I get to this 2.5, that means that I'm on my second rotation here. So this is really 2.5 seconds, so I'm back at 11. And then at 3, I'm at 4 inches from the ground. So if I'm trying to identify the period of the function, that would be the length of one cycle. And because we are dealing with a rotating object, that length of the period is how long it takes us to complete one revolution. So as I'm looking at this, if I'm going around 1 time, that takes me 2 seconds. So what that means is my time is going to continue to increase depending on how long I'm on the bicycle, but my y values are going to continuously rotate between this 4 and 18 seconds depending on where we're at in this cycle. So the period of this function is going to be 2 seconds because that's how long it takes me to complete 1 full revolution. So then to get our graph, we're just using this table here and plotting our points. So time should always be horizontal, and then our height is going to be vertical. Okay. Now when we're trying to pick our scale, it's not going to be the same because if I'm looking at my time, I'm going between 0 and 3 seconds, and my height is much bigger. So I need to pick a scale that's going to fit each part. So most of the time when we're choosing that, if we are dealing with time, we're going to pick whatever the interval is happening in our x column. So for these, I'm going to count by halves since I'm increasing by half a second each time. And as we mark these, we can fill in every single interval, or we would just give enough information so that way when someone looks at our graph, they know what we would be counting by. So I can put my 1 here, 2, 3, 4, 4, 5, 6. And then I'm going to choose to count by 3s for my y since I don't have a lot of vertical space. But we could also count by 2s. 4 would be acceptable. We could do 1s, but we're going to have a lot of tick marks since we need to go up to 18. So I'm gonna choose to count by 3. So 3, 6, 9, 12, 15, 18. And then now I'm just filling in my points. So at 0, I'm up at 18. Half a second, I'm at about 11. 1 second, I am at 4. 1.5, back to 11. 2 up at 18. 2.5 is at 11, and then 3 is down at 4. Now, if I wanted to continue my graph off of my chart, I'm just going to keep following this pattern. So then I would be up there at 11, 18, 11, 4, and I can keep going forever. And then I'm just going to connect my points in kind of a wave pattern. Now, as we look at this, we have to think about what our domain could be and what our range is going to be. So for the domain, that means I'm asking you for all the x's on the graph. So we have to use what we know about domain as well as the context of the problem, since we're dealing with something that's happening in the real world. So technically, I could continue this wavy pattern backwards if I wanted to, but because we're talking about time, that wouldn't make sense. So we're not allowed to have negative time, because as far as I know, we haven't invented time travel yet. So when we're doing our domain, we have to start at 0, and then this pattern is going to continue to happen until we get off this bike. Now, we weren't told what time that would be, so when I do my domain for this, for now, I would write it as 0 to infinity. But let's say that we were pedaling the bike for, 2 hours. So if I know that, then I would need to adjust my domain to reflect that. Now I'm going from 0, but I have to be careful because my time is in seconds. So I need to list my domain in seconds then. So for 2 hours, to change it to seconds, I would have to multiply that by 60, which would then put it into minutes. And then I would have to multiply by 60 again to get it to seconds. So 7,200 would be my domain if I knew that I was going to be on this bike for 2 hours. But they didn't tell us that part, so for right now, I'm just going to leave it as this infinity. Okay. And then for the range, we're just listing what all of our y values are between. So they are between this 4 and 18 inches. So we will always be between 4 and 18 inches off the ground. Okay, so if we keep going, again, go ahead and pause the video and read through number 4. Okay. Now for this question, it's not asking us to graph this time, it's just asking us what the period is of this function. So it's important that we can kind of pull out the important pieces and then ignore the extra information. So we were told that we have a diameter of 18, and then 4 revolutions happen in 1 minute, and it's asking us what the period of our function is, and then this part is describing what that function means. So it's the height of one spot on the outside edge of the wheel over time. So this last part is just extra information that we don't really need to pay attention to for what the question is asking us. Same thing with the diameter here. So for this 18 inches, that's just referring to our possible height of this. But because we're asked for the period, that's our horizontal distance, which is going to be dealing with this time. So what we need to do is figure out how long it's going to take for just 1 revolution. So to do that, we would set up a proportion. And there's a couple different ways that we can set up the proportion. So I know that I'm going to have 4 revolutions for every 1 minute. So if I flip that around, so 1 minute gives me 4 revolutions, that's fine. But where I put my labels matters. So since I've set up my fraction, when I set it equal to what I'm trying to figure out, the number of revolutions has to stay in the top part of my fraction, and then the time will be in the denominator. So again, we are trying to figure out how long it's going to take for just 1 revolution. Okay. And again, we have context, so we need to think about what that means for our answer. So when I do my calculation, I would expect that my x value is going to be smaller than 1 since I'm only going around once. And when we're talking about time, we don't measure time in decimals. We measure it in seconds. So that means then that I really should figure out what this would be measured in for seconds here. So I'm going to do that next. So I would still have my 4 revolutions, and then 60 seconds is equivalent to the 1 minute. And I'm still trying to figure out how long it's going to take for just 1 revolution. Okay. So now I'm ready to do my cross multiplication and then divide. Okay. So if I do that, 4 times x is 4x, 1 times 60 is 60, and then I'm dividing by 4. So my x is going to be 15 seconds. So that is the length of 1 cycle for this function. So it's going to take me 15 seconds to go around once of whatever I'm revolving around. All right, so again, I would like you to pause the video, read through number 5. So as we are reading through this, we are given a Ferris wheel. So I'm going to draw a circle here. And our Ferris wheel has a 40-foot diameter. And it is going to be 5 feet off the ground. And we complete 1 revolution every 60 seconds. And we are supposed to come up with a graph of what's happening. So remember, time needs to be along our horizontal, and then our height is going to be along our vertical. Okay. So I'm going to make a T-chart here to help me figure out our time and our height. Okay. So as I'm looking at this, I need to figure out easy heights on my Ferris wheel. So at the bottom here, I would know that my height would have to be 5, and our problem is telling us that we are getting on at the bottom of our Ferris wheel at time 0. So that means that at 0 seconds, I'm 5 feet above the ground. So now I need to figure out some more heights, and we want to pick the ones that are easy and definitive. So that means that I can't really pick this one here because that would require a lot of calculation to get an accurate height. So if I'm thinking about the radius of this circle, that means that from the center to here is also 40, and then if I'm going from the center to the top, that's 40. So this total length then would have to be 80. So if I'm at the very top of the Ferris wheel, that total distance all the way down to the ground would have to be 85. So I'm taking the diameter of that Ferris wheel plus 5 to get that height. Okay. Now I'm going to need some more points to get an accurate picture. So another easy thing for me to calculate would be in the middle of my Ferris wheel, because I know that this distance right here would have to be 40, and then I'm going another 5 feet down to the ground. So this height is 45. And then same thing on this side, this height is also 45. Okay. So now I need to think about how that relates to time. So in the problem, I am told that 1 revolution is every 60 seconds. So if I'm starting down here and I go around 1 time, that total time is 60. So the way I've kind of measured my circle here is I've cut it into fourths. So if I do 60 divided by 4, that means that at each of my points here, I'm just adding 15 seconds. So at 15 seconds, I should be at 45 feet. At 30 seconds, I'm going to be at the top of my Ferris wheel, so 85. 45 seconds, I'm now here. So again, I've rotated here at 45, so my height will also be 45. And then at 60 seconds, I'm back down at the bottom. Okay. Now, if I think about this, my time is going to continue to increase. And notice in our problem how it tells us that we have 2 revolutions. So that means for my domain for this, I'm going from 0, and then my time would be 60 seconds for one revolution, and then if I add another 60, it's going to be 120. And then my range has to be between that 5 and 85. Okay. So now I'm going to pick my scale. So I'm going to count by 15s. So this is 15, 30, 45, 60. And then I have to keep counting by 15s until I hit 120. So 75, 90, 105, and 120. And then for my height, again, I'm just picking a scale. So yours could be different from mine. So I'm going to choose to count by 10s. So I just need to make sure that I'm going at least up to 85. So 10, 20, 30, 40, 50, 60, 70, 80, 90. And now I'm just plotting those points, and we're going to connect them together into that wave. Now, because we're doing this by hand, it's not going to be completely accurate, so it's important that we are making sure that we are labeling things correctly and including that domain and range that I wrote off to the side, as well as our t-charts. So having all of that information will help give an accurate picture to whoever is looking at our graphs. And when we are connecting them, it does need to be a wave. It should not be pointed peaks. So again, this is where it's important to know that I did this by hand. This is not actually at 0. It's going through this point. Okay. All right, so for the next one, again, I would like you to pause the video and then work through that last problem. And I will provide the answer to it in our next video.